So it's time to hear Rory Lucyshyn-Wright talking about a long title, structure semantics. Thank you.
Thanks very much. And I'd like to thank the organizers and the scientific committee. And I wanted to emphasize that this is joint work with Jason Parker. So I'll start off with a brief historical survey of some works and settings for theories and monads. And in each setting we'll see a particular full subcategory, the objects of which play the role of arities. And we'll see a kind of theory and a corresponding kind of monad. And so, first of all, of course, we begin with Leviere's introduction of algebraic theories known as Levier theories. And there, one can see the arities as being finite cardinals, or we can work with all finite sets as well. And Levier introduced this notion of algebraic theory or Levier theory, and these are equivalent to finitary monads on the category of sets. And Levier showed that the semantics functor has an adjoint known as structure, and we'll look at this in detail in a general setting. And Linton, in 1966, provided an infinitary notion of theory where the arities are arbitrary sets. And these can be called Linton's varietal theories. That was the name used in the paper. And they are equivalently described as arbitrary monads on the category of sets. And Linton also established a structure semantics adjunction. And Dubout, in 1970, generalized this to the enriched setting, but also, so he principally concentrated on the case of monads and theories based on the V category V itself, but he also briefly treated a generalization of this to an arbitrary V category, C, and defined a notion of C-based V-enriched theory. And these correspond to, they're equivalently described as arbitrary V monads on C. And there the arities are arbitrary objects of C, so we see the subcategory being the entire category C, V category C. Borsa and Day considered enriched Levier theories in which the arities are finite cardinals, discrete finite cardinals, or equivalently, the finite copowers of the unit object, n times I, as we see there, constitute a full subcategory of V, and they worked in the setting of a pi category. For example, any complete and co-complete Cartesian closed category V. And these theories that they defined correspond to strongly finitary monads on V, as studied in the Cartesian closed case with further contributions from Kelly and Lack in 1993. And Borsa and Day did establish a structure semantics adjunction. Now, Kelly and Power considered finitary V monads on a locally finitely presentable V category enriched over a locally finitely presentable base V. And these finitary monads correspond to the enriched Levier theories introduced by Nishizawa and Power, and earlier in the special case of C equals V by Power. And there in this setting, the arities are the finitely presentable objects of C. And I would mention that I don't believe that a structure semantics adjunction for these theories was developed. In 2011, Lack and Rositsky treated a setting where we start with a class of weights, phi, a locally small class of small weights satisfying their axiom A, and considered a locally phi presentable V category C, and in that setting defined Levier phi theories, which are equivalent to phi accessible V monads on C. And so there the subcategory of arities is the 5 presentable objects, C5, 5 presentable objects of C. And one thing to emphasize in this setting is that V doesn't have to be locally presentable. This is an important point. Despite the terminology, the base V category the base of enrichment V does not have to be locally presentable. But I haven't seen a structure semantics adjunction for these theories. And in 2016, I introduced the concept of eleuthermic system of arities, which is a given full subcategory of V, satisfying certain axioms. And I considered J theories in that setting. And these are equivalently described as J area V monads on V. And so this setting captures all of the preceding settings as examples or special cases. But there hasn't been a structure semantics adjunction developed for this one. And in 2019, Burke and Garner considered an arbitrary small subcategory of arities, J, small full subcategory of a V category C that's assumed locally presentable, and over a base V that's assumed locally presentable. And they considered J theories in a sense that generalizes the preceding one to the setting where we have C-based theories. And these correspond to, are equivalently described as J nervous V monads on C. And so this last setting of Burke and Garner has an impressive generality in that we can take an arbitrary small subcategory of arities in C. But the scope of its applicability is limited by the assumptions that J has to be small and that C and V have to be locally presentable. So as a consequence, among the previous listed classes of examples, the only ones that are captured in full generality by this setting of Burke and Garner are the ones of Kelly power, and Nishizawa power in the locally finitely presentable setting, and in particular the classical case of Levere. So what we would like to do and have done is to put all of these, including the prior examples, but also the Burke-Garner example, under a common roof, and also to develop a structure semantics adjunction that will apply to all of these settings. And as you can see, we don't have structure semantics adjunctions previously developed in many of these settings. But furthermore, we'll very much go to a setting where the categories involved don't need to be locally presentable, and the subcategory of arities doesn't need to be small. And I've also wanted to mention some further works that are relevant, but that we a priori neither generalize nor specialize, some of which are going in different directions in certain senses. We have Outline of Functorial Semantics by Linton, Street's Formal Theory of Monads, the Berger-Méliès-Weber setting of monads with arities, and Avery's study of structure semantics, and Fuji's general setting for theories as monads in a monodal category, which we don't know that will capture the case of the Burke-Garner setting. And quite recently we have Arker's work and the work of Arker and McDermott, and we're quite optimistic that it may be possible to take some of these results and put them in that setting. But this is not yet known. Okay, so our setting that we'll start with is a symmetric monodal closed category V with equalizers. And then a subcategory of arities in a V category C is a fully faithful and dense V functor J from a V category J to C. And this is dense in the enriched sense. The full subcategory J does not need to be small. Now we can consider the nerve functor for J which sends each object A of C to the presheaf that you see there, C J blank A, which is called the J nerve of A. And that V functor category that you see there might not exist as a V category, but it will exist as a V prime category for a standard universe extension V prime. And the objects in the essential image of NJ, these are certain presheaves that are called J nerves. And we have the following definitions. A J pre-theory is a V category T with an identity on objects V functor, tau, from J op to T. So the objects of T end up being the objects of J. And then among these, the J theories are those J pre-theories that satisfy this further condition, that for every object T of T, when we look at the following V functor, it is required to be a J nerve. And then we say that T is a J theory, not just a J pre-theory. Then we can consider the category of J theories as a subcategory of the category of J pre-theories, and this is a subcategory of the co-slice under J op in VCAD. And these notions of theory and pre-theory under different names are originally due to Linton and Deers, and were employed in the enriched context by Burke and Garner under the above names, which we maintain. We can consider algebras for theories. A concrete T algebra, which I'll simply call a T algebra, is an object A of C, the base V category, equipped with a V functor M from T to V, such that the restriction of that M along tau is precisely the J nerve of A on the nose. And so consequently, these algebras, T algebras, are the objects of the pullback T-alg, as we write it here, the following pullback, taken in V prime cat, because so far we don't know that this is a V category, but we'll be interested in cases, particularly in cases where T-alg is a V category. And this notion also goes back to Linton and Deers and has been employed in the enriched context by Burke and Garner with the above name, concrete T-algebras. Now, the axioms that we'll impose that we've found which seem to make everything work are the following. We say that the subcategory of arities is amenable, respectively strongly amenable, if this forgetful functor ut from TL to C is a right adjoint V functor for each J theory, respectively each J pre-theory T. And so this is a very brief way of putting it. So what's meant here is that TL exists as a V category, it's a V category, and this V functor has a left adjoint. And actually, yes, okay. All right, so this is these are the axioms that we'll work with, and of course, one being the weaker and the other the stronger. And we'll develop structure semantics, a structure semantics injunction in this setting. And to get started with this, we'll need to restrict to certain V categories over the base category C. So certain V functors down to C. Just as Levere restricted to categories over set that are called tractable V categories. Here in this setting, we say that a V functor, G from a V category A down to the base category C, V category C, is J tractable if the following weighted limit exists in C for every object J of J, every arity J. So this is the notion of J tractable V functor or J tractable V category over C. And these form a full subcategory, J tractive C, full subcategory of the slice, V cat over C. V cat over C is the category of V categories over C. And among these we find the J tractable V categories over C. For example, if G is a right adjoint, then it's necessarily J tractable. But more generally, if J simply has a J relative Right. So if G simply is a J relative right adjoint, then that's enough to imply that G is J tractable. And we arrive at the following first one of our general structure semantics theorems in this setting. If J is simply amenable, then we obtain an adjunction of the following form. Recalling that J tract of C is a full subcategory of the slice V ket over C. So here we have the semantics functor that sends each J theory T to the V category of T algebras with its forgetful V functor to C. So that's the semantics functor, and it has a left adjoint structure which sends each V functor G down to C, each tractable V functor G down to C, to a theory that is called structure of G, the J structure of G, generalizing Lemaire's notion of algebraic structure. And what this J theory is, it's a J theory, so its objects are the objects of J, and the Hom objects are defined in the following way. So we take the Hom between certain V-valued functors here. And of course we can look at how this specializes to various cases. Furthermore, the semantics functor is fully faithful. So actually, J theory's op is a reflective subcategory of J tract of C. So this is in the case where J is assumed to be amenable, the weaker of the two axioms, but if we go to the stronger axiom, suppose that J is a strongly amenable subcategory of arities, then we obtain not just what we had in the previous step, we have that, but we also have the following idempotent adjunction between now the larger category of pre-theories and J tractable V categories over C. And again, this is defined in the same sort of way, the semantics functor and the structure functor. And the fixed points on the left-hand side are the J theories. And so then we'll have an equivalence between those and the fixed points on the other side. So what are those? Those will be J algebraic V categories over C as we'll define. So for what we'll do, for the rest of what we'll do here, we'll suppose that the subcategory already satisfies our axiom of being amenable. And we say that a V category over C is J algebraic, or respectively strictly J algebraic, if A is equivalent to T alg in the pseudo-slice 2 category. Respectively, A is isomorphic to T alg in the strict slice category, V category over C, for some theory, J theory T. And these J algebraic V categories over C form a full subcategory of the slice. Strictly J algebraic we'll look at here in terms of defining this category, subcategory of the slice category over C. And we can show, as a corollary, of course, to what we've just said, that we have a dual equivalence between the category of J theories, theories J, and the category of strictly J algebraic V categories over C. But now we can inquire, these fixed points, and of course the ones that are of the form T alg, what are they? How can we characterize them? How can we characterize them intrinsically? And here we have an intrinsic characterization of these. A V category A over C is J algebraic if the following conditions are satisfied. First of all, G has a J relative left adjoint F. That's the first requirement. J relative left adjoint F. And secondly, that when we look at the full subcategory of A, consisting of the free objects on objects of J, the arities, free objects on those, they form a full subcategory. We require that this be dense. And then thirdly, we require that a presheaf X from AF op to V is a JF nerve, so a nerve for the previous inclusion, if and only if its restriction along the following canonical functor from J to AF is a J nerve. So that third condition. So we have a characterization here of J algebraic V categories over C. And one thing that's quite interesting about this is that we'll see that these V categories over C are monadic. But we don't really see conditions here that are reminiscent of monadicity theorems, except perhaps just the J relative left adjoint, which is pretty weak. And yet we do get a kind of monadicity theorem here that looks quite different from other ones. And so we can ask, what are the monads determined by these monadic adjunctions? And so for this, we'll recall a definition of Burke and Garner. A V monad T on C is said to be J nervous if it satisfies the following conditions. That the following V functor is dense, where here we write J sub T for the full subcategory of the Kleising category on the objects of J. So we require that be dense, and that a presheaf X from JT up to V is a JT nerve, if and only if its restriction along the canonical V functor from J to the JT rather is a J nerve. And so if we think about this we can characterize this equivalently in the following way in terms of our intrinsic characterization theorem for J algebraic V categories, which we've just seen. And arguably this sheds light on this concept that equivalently, this is the requirement that the Eilenberg-Moore forgetful functor satisfies conditions 2 and 3 in our characterization theorem for J algebraic V categories over C. And so consequently, we get the following observation that T is J nervous if and only if this V functor is J algebraic. So now we'll look at the monad side of the picture here of this setting. We'll define the category of J nervous V monads on C, which we'll denote in the following way. And we obtain the following theorem, that first of all, the category of J theories embeds as a co-reflective subcategory of the category of all V monads on C. And the essential image of this is precisely the J nervous monads, so we get an equivalence between J theories and J nervous monads on C. And then in the strongly amenable case, we get an idempotent adjunction between the more general pre-theories, J pre-theories, and arbitrary V monads on C. And so this generalizes a result of Burke and Garner to the present setting. And now we can ask, well, what subcategories of arities are amenable and strongly amenable? What classes of examples can we apply this to? And in brief, we can apply this to all the examples that we saw earlier. But how do we show this? So first of all, one substantial class, actually quite broad class of examples here is provided by the following theorem, that every eleuthertic subcategory of arities is amenable. So in particular, we recover almost all of the previous examples. We have the identity functor on an arbitrary V category C, so we get arbitrary V monads on C. Secondly, we have the kind of finite discrete arities employed by Borsa and Day, and Kelly and Lack. In the setting of a pi category V, for example, any complete and co-complete Cartesian closed category. And thirdly, in the locally presentable world, where V is locally alpha presentable and C is a locally alpha presentable V category, we can consider the alpha presentable object, C alpha, in there. And so we get that example being eleuthertic and hence amenable, as all these examples I'm discussing are. Then we have also the setting of Lack and Rositzky with a locally small class of weights, phi satisfying axiom A, and locally phi presentable category. But still this class of examples here doesn't yet capture the Burke-Garner setting. And so one way of doing this, among two that we have, is the following theorem, that if we take V to be a locally bounded closed category, and we suppose that C is the category of models for a small phi theory for a class of weights phi, then we can show that every small subcategory of arities in C is strongly amenable. And so this way we get the following examples. Not only do we get the locally presentable setting of Burke and Garner, But we can also do things like the following: take C itself to be V, a locally bounded closed category. So this way we get lots of categories that aren't locally presentable, such as convenient categories in topology and analysis. And then here, this last result mentions a theory of presentations of J theories that we've developed and presentations of J-nervous monads, which I can comment on after the session. So thanks very much. Here's a list of relevant references that I mentioned.
Thank you for a very interesting talk. Are there questions or comments?
Maybe I just said that it's quite impressive that you got rid of all the size conditions from what Richard and I did for the maths and theories. So it seems like you freed all our results of those extra convenient assumptions. So,
Thanks very much, and we're also very much impressed with your work there with the added type of generality that it.
If there are no more questions, we thank the speaker again.